Good morning. This is Mr. Minnick, and I am joining my one class. This is fourth period statistics, February 7th. And normally, as part of our class, we check the holiday. We didn't check the holiday yesterday. But today, we're going to look at Chapter 4, Section 6, the multiplication rule. So here it is, Chapter 4, Section 6, the multiplication rule. The multiplication rule. And then I think there's either a colon or a semicolon. There's certain things that in life I think that just the names that they use bother people. For instance, the word integer. When parents of seventh grade students in math hear the word integer, they cover up their ears and they go la 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 la. La. I don't get it, right? It's scary. The word colon scares me. So anyway, the word colon, because they use half of a colon. Or is it a semicolon? They use a semicolon here. So semicolon, independence with an asterisk. So I forgot the semicolon. So semicolon, independence. Independence. I wonder if this will recognize my semicolon. It won't. Well, maybe it did. I don't know. Kind of close. Independence. So before we move on any further, maybe it would be a good idea to do what? To sing a power ballad? Um, Give me an example of a power ballad. Home Sweet Home by Motley Crue. I don't know that one. Here I Go Again by Whitesnake. I kind of know that one. But the problem is that it won't turn out good in the video quality. We're going to sing, I believe it. We got to sing a song that everybody knows. We will sing on this video before it's all said and done, I promise. I promise. Okay. So, when you see independence, maybe you think of the greatest country in the world. America. Bad word. Freedom is the only way, yeah. How many stars are on the flag? A lot. Okay, that's not the kind of independence we're talking about. That's not the kind of independence we're talking about. Um, we're talking about independent events. Independent events. Okay. So, events are just simply things that happen. I really like Mountain Dew. Mountain Dew Code Red. So I've got a bottle of Mountain Dew Code Red sitting here. Too bad they didn't make pop bottles in glass. I miss glass containers. Okay. They have shape. Oh, I've seen that. Yeah, they do. They did bring them back. You're right. They did bring back the pop bottles in glass. So we've got a bottle of Code Red Mountain Dew. So suppose event A, in honor of somebody in our class, suppose event A is taking a sip of take a sip of Code Red Mountain Dew. Okay? So we're going to take a sip of Code Red Mountain Dew. That's event A. Event B is take a sip of regular Mountain Dew. Okay, so we need another bottle of Mountain Dew as well. So I should just clone this and do that, huh? So I could clone that, and we'll make this, try to make it as close to Mountain Dew. Is that pretty close? That looks like the lime Mountain Dew. So we got Code Red, Code Red, and then we've got Mountain Dew. Have I ever told you about a former employer of mine that was so deathly in love with Mountain Dew? it was the funniest thing. We were doing an inventory, and every day he brought a 12-pack of Mountain Dew into work with him at Radio Shack when I worked there, and he would have it beside his desk, and we were doing inventory, and he said, "I love Mountain Dew. I drink Mountain Dew all the time. Here, have a Mountain Dew." So I had a Mountain Dew. When somebody offers you Mountain Dew, you got to take it. So anyway, he had about 4 of them all throughout the store because we were doing inventory where you count everything in the store. And he freaked out. He said, "Where's my Mountain Dew? Where's my Mountain Dew? I had one right there over there by the speakers. It's not there." He handed me a $50 bill. He's like, "Here, go to Giant Eagle, get some Mountain Dew. We have to have Mountain Dew." So I went to Giant Eagle and I brought back like um, 5 cases of Mountain Dew. I said, "I wasn't sure how much to spend because you gave me a 50." He's like, "No, that's good. I'll drink it. Trust me, it's fine." So anyway, um, we've got 2 events: taking a sip of Code Red Mountain Dew and taking a sip of regular Mountain Dew. Those events are either independent or they're not. What are they? I'm hearing independent. Independent, if we think back to when we talked about independent events, means that the outcome of one doesn't affect the outcome of the other. So if we drink out of the one bottle of Code Red Mountain Dew, does that affect drinking out of the other? It might affect what goes in our belly, but it doesn't. The bottles don't affect each other, right? So so does that make a little bit of sense? What independent events are? Events where the outcome of the one doesn't affect the outcome of the other. So if we're talking about how much Mountain Dew is in the Code Red bottle versus how much is in the regular bottle, event A, if we sip some out of the Code Red bottle, it's going to take some out of that. Event B, sipping some out of the other one, the drinking out of the one and drinking out of the other, it might affect us. It might affect my manager at Radio Shack because he'd probably go ballistic over Code Red. I know that there's a teacher in this building that loved a certain kind of soft drink that's not available anymore. So anyway, independent events can't happen at the same time. Okay, so what we're going to be talking about today is this: the probability of A and B. Okay, so it's kind of difficult to talk about probabilities with Mountain Dew because Mountain Dew's just, I don't know, food's always a bad thing to talk about. So maybe we should talk about cards, playing cards. We talked about those before. So let's let event A be draw a 7 of spades. Draw 7 of spades. And event B is to roll a 3 on a number cube, or a dice, if you would. So the probability of A and B, there's a certain formula that we're going to use, and if the events are, depends on if they're independent and dependent, we'll have to read the book because I honestly can't remember, but I do know that sometimes to find that probability, what we do is we kind of multiply, and you'll see why. Let's draw a Venn diagram here. A 7 of spades out of a deck of cards, what's the likelihood of that happening? It's real small, isn't it? It's like 1 out of 52. So if you could imagine splitting this up, there's just a wee little chance of that happening right here. All right? That's a 1/52nd, 1 out of 52. That's a really small amount. Rolling a 3 on a number cube, we have a greater chance. What's the chance there? It's a 6th. It's 1 out of 6th. So 1 out of 6, trying to picture how big that would be. A third would probably be like that, so half of that would probably be a 6th. Okay, so 6th would be about that much. So for both of those to happen, we're going to take the chances of the one happening and the chances of the other happening. And what happens, it's weird, and there's probably better animations than this, and maybe we'll go to the internet and look up a YouTube video or something, I don't know. But anyway, what happens is we have a small chance of the one happening, a small chance of the other happening, and for both to happen at the same time, the chance is even smaller still. And the reason that happens is because we end up multiplying these. So it's the probability of A times the probability of B. So in this particular instance, it would be 1/52nd times 1/6, which would be 1 over 312. And that's not very likely. So maybe we should try our luck today. Anybody feeling lucky? I actually have, the TI-84 where I can roll a number cube and draw. So if we do this experiment 312 times, it should happen, right? In theory. In theory. I will seriously scream really loud if this happens, if we get a 7 of spades on the first try and in a 3 on a number cube. So I want to go to, what are we going to? Apps. Isn't it probability? The probability app. Here we go. It's probably the probability app. I wonder if this will let me open up a second calculator. I don't know if it will. I'm going to keep my fingers crossed here. I already got one open. So on the one, we're about to draw cards. Let's see. Settings. One deck. Replace. Yes. 52. Okay. I got to promise myself that I'm going to do something crazy. How about I do the worm? Try to become the principal of the school. I would not. I would not do that. Okay, so our volunteer's going to come on up and draw for us. We're looking for a 7 of spades. Just press the draw button, which is the window button, I guess. Yeah. Oh, well, is that a spade though? It was a jack of spades. Okay. All right. So let's go and we'll draw. We'll roll the dice now. Okay. Come on, 3. Well, we were close. We were close. Is that worthy of a cartwheel in the hallway? No. Close. We weren't quite close enough. So maybe we should do that 312 more times. Or maybe we should just realize that in theory that should happen if we did that 312 times. Will it? Maybe, maybe not. Will it happen on the second try? It could, and then it won't happen for the next 310. It doesn't work like that, but in theory that's what should happen. Does that make sense? Okay. Let's go back to the book. I'm not a big fan of reading. Um, so they've got a conditional probability formula here. And we actually had written this before. The conditional probability rule is used to compute conditional probabilities in terms of unconditional probabilities. So we better write that down. The probability of B given A is the probability, what did they say? The probability of A and B over the probability of A. Is the probability of A and B over the probability of A. So when we looked at contingency tables, we talked about conditional probabilities and the like. We've actually seen this formula. We've used it a couple times. So I hope we don't just have a rerun of what we already looked at. Let's go to the next page. It was all over the probability of A. So they're saying what they're going to do is multiply both sides of the equation by the probability of A. And basically what they're doing is they're kind of solving it for the probability of A and B. I see what they're doing. I see what they're doing. They're going to try to do some algebra. To isolate this right here. Okay? So isolate that. So if we do that, we multiply by the probability of A, so that cancels out that. We multiply by the probability of A. So what they're saying here then is this new formulae for the probability of A and, oh, I'm getting ahead of myself. And I just dropped the eraser as if it were hot. The probability of A and B is equal, it's contagious. Now somebody's dropping their cell phone. It's the probability of A times the probability of B given A. So when you're asked to find the probability of this and that, realize that you're probably going to be multiplying. Because the probability of one thing happening and something else happening, it's a small chance and a smaller chance, and it's a combination of two small chances. So you take a small chance, you take a smaller chance, and you combine them by multiplication, and it becomes a lot smaller still. And it's kind of counterintuitive to what you might think. The probability of this and that happening, you might think, well, the word and means plus. It does in other contexts, but not in the context of probability. Does that make sense? That it's a little counterintuitive. The word or, in terms of probabilities, that's where you add. So, okay. So we got that formula. So the probability of A and B is the probability of A times the probability of B given A. All right. Again, I'm not a big fan of reading, but let's see what this says. The conditional probability rule and the general multiplication rule are simply variations of each other. On one hand, when the joint and marginal probabilities are known or can easily be determined directly, we use the conditional probability rule to obtain conditional probabilities. On the other hand, when the marginal condition and conditional probabilities are known or can be easily determined, we use the general multiplication rule to obtain joint probabilities. I'm not going to comment on the example number that follows that last sentence, but here we go. The general multiplication rule. You can't make this stuff up. I didn't make this up. This is somebody else's book that they wrote, okay? Okay. So they're talking about Congress. Congress has been making the news a lot lately. The U.S. Congress Joint Committee on Printing provides information on the composition of the Congress and the Congressional Directory. For the 110th Congress, 18.7% of the members are senators. 49% of the senators are Democrats. And currently, I guess that means, and I think the Congress now is Republican dominant, isn't it? And there's fights in Washington because of that. Okay. So the question is, what is the probability that a randomly selected member of the 110th Congress is a Democratic senator? So this is a real nice example. Event D is being a Democrat. Event S is being a senator. So they're using the formula where we take the probability of S and D equals the probability of S times the probability of D given S. And notice the probability of the one is about 18.187. The probability of the other is 0.490. Multiply them and we get a real small chance. So I think that example is pretty cool. I'd like to try an exercise on this. You think we should go for it? See if we can jump all the way to the end. Jump all the way to the end and try an exercise like this. Maybe, just maybe, we'll even try a math Excel problem like this. All right. So here we go. 4.123. Problem number 123 in chapter 4. Regarding the general multiplication rule and the conditional probability rule, state these two rules. Indeed. General multiplication rule. General multiplication rule. I don't know if we saw this earlier in the chapter or not. I'm pretty sure I've written this down. This is the probability of A and B equals the probability of A times the probability of B. Now the other one is the conditional probability rule. The conditional probability rule. And that's the one that we just wrote, which is the probability of A and B is the probability of A times the probability of B given A. Do they look that much different? Really, the only difference is the conditional probability rule is the second thing we're multiplying by. It's just B given A, so we kind of have to assume that A happens. Okay. All right. Well, anybody else feel like watching the Olympics tonight? I think I'm going to become a curler. I seriously want to do curling. I don't know what kind of shoes they wear, but I would get some really fancy Nike curling shoes. The curling things are the big cement looking things. Yeah, they have a handle on them and they kind of slide on one knee and it's essentially like similar to bocce, similar concepts to bocce, just on ice. Okay, so the next example, the general multiplication rule in Professor Weiss's introductory statistics class. The number of males and females are shown in the frequency distribution. Okay, um, two students are selected at random from the class. The first is not returned, so there's no replacement. You'll hear the buzzwords replacement and without replacement. So there's no replacement. Um, And then find the probability that the first student selected is female and the second is male. So let's see how this example is gonna shape up. So F1 is the event that the first student is female. M2 is the event that the second student is male. So we want to determine the probability of F1 and M2. So here they're using the general multiplication rule, and they multiply the probability of F1 by the probability of M2 given F1. I have a feeling that I might have written the general multiplication rule down wrong. I have a feeling that we're missing something. I think something's missing. I really do. Can anyone help me clear up my my mental fog right now? Because they're saying that the general multiplication rule is the probability of the first thing times the probability of the second given the first. So I think I am misleading you all when I have this. Where's this? I guess my question is, where's the conditional probability rule at? We got the general. I think we got the names mixed up. Where's this conditional probability rule? Ah, I see. I see. Do you see what I see? Do you see what I see? I think I see it. I see the forest for the trees. This is in the wrong place. Yeah, that should be the general rule. So it's not that much to change, and I do apologize for misleading you, but I'm glad that we're getting this figured out. It's a good thing that they had us do that problem. The general multiplication rule says we do multiply, but the conditional probability rule was the one that we saw in the last section. This says the probability of B given A is the probability of A and B divided by the probability of A. That's the conditional probability rule. So I guess this kind of leads me to a real good essay question. What's the difference between them? It reminds me of Luke Skywalker and Darth Vader. Not the Christmas presents about him. What'd you say? He is the Father. Yes, yes. Which one? Which one is the paternal or maternal unit of the other? When we did this algebra stuff, we started with the one thing and we ended up with the other thing, right? We started with the conditional probability rule, right? This red thing here that we started with, this is the conditional probability rule. And when we do a little bit of algebra to it, then we ended up with this general multiplication rule. Okay? So if you missed it, if you missed that ship that has sailed, the passengers aren't getting sick, although they might want to go home. Although they might want a refund. What do we got? Yeah. So what we're saying here is that the general multiplication rule is born from the conditional probability rule. If you take the conditional probability rule and you solve it for the probability of A and B, then that's where the general multiplication rule comes from. So you're welcome. So basically what's going on here is they're the same rule, they're just in different forms. It's just an equation solved for a different variable. Does that make a little bit of sense algebraically? Okay. Questions, comments, concerns, short debates? Long debates? Well, we got to sing that song before this is all said and done. Real quick, let's see if there's anything else in the book here. We looked at example 420. We looked at example 421. We multiplied. Ooh, that looks fun. Tree diagrams. Ooh, tree diagrams. That's interesting. I wonder if any of those are going to show up in Math Excel. Anybody try the 4.6 Math Excel homework yet? Is it there? Is it even online? Is it on the line? Oh, here's something that we probably ought to write down. Event B is said to be independent of event A if the probability of B given A is the probability of B. That would be good to write down. Event B is said to be independent of event A if the probability of B given A is equal to the probability of B. Let's write that down. Event B is said to be independent of, I can spell, independent of event A if the probability of B given A equals the probability of B. We're to assume that A happened. If A happened, the probability of B, assuming A happened, is equal to just the probability of B, meaning A doesn't affect the outcome of B. Meaning irregardless, chuckle, irregardless of what happened with A, the probability of B is the probability of B, whether A happened or not. Does that make sense? Drinking out of the Code Red Mountain Dew, regardless of what happened with the regular Mountain Dew, it's the same probability. So I think we got all the good formulas that we need down. Here I go again on my own, like a drifter I was born to walk alone. Well, they got this face card example here. F is the event getting a face card. K is the event getting a king. H is the event getting a heart. Part A, they want us to find whether K is independent of F. Whether K is independent of F. So the probability of getting a king by itself is 1 out of 13, right? If we assume it's a face card, the probability of getting a king, assuming we got a face card, is 1/3. For those two events to be independent, the probability of the one given the other would have to equal the probability of the one. Are they independent? No. Does that example make sense? Kind of. I know we rushed through it. I think I'm ready for Math Excel. I think I'm ready for some coffee. And I think I'm ready for dancing school. Because I want to learn how to dance. That's my new goal. So here we go. 4.6 homework. I guess it's not on the line. It'll be down the line next week. Are there any questions about anything we talked about today? Perhaps we should make our own example, and we'll end up with this. Example. Event A. Event A is playing a Miley Cyrus song. In Mrs. Minnick's car. Okay, so let me draw you a picture of Mrs. Minnick's car. She's got a 6-disc in-dash CD player. I got to drive it today to school today, by the way. I'm so pretty stoked. It's a 6-disc in-dash CD player. That doesn't look like a CD player, but here we go. Disc 1 is Toby Mac. Disc 2, soon to be discarded for reasons I can't disclose, Katy Perry. Disc 3 is Her Loving Husband, his original music that she always skips over and doesn't listen to. Disc 4 is that one guy that looks like Evan Skosik's sister, Jason Castro. Jason Castro, or Evan Skosik's sister looks just like Jason Castro. Disc 6 is Miley. Okay, and disc 5 is Family Force 5. Family Force 5. Okay, so let's just, for sake of simplicity, let's assume that each CD has the same number of tracks on it. Okay, so event A is playing a Miley Cyrus song. All right. So let's think about, well, let's not even calculate that probability yet. For sake of simplicity, we're going to assume the same amount of tracks are on each. Okay. Event B is playing a country song. Okay. Playing a country song. I will be honest with you, I have not written any country songs that I know of. Miley Cyrus might have a country song. So for sake of argument, let's assume that this is an old Miley CD. Okay, good call. Thank you. Family Force 5 plays rock and roll / rap / funky R&B type Christian music. Okay, Jason Castro plays contemporary Christian worship music. The original song that's in the CD player that I wrote, contemporary Christian music. Katy Perry, we'll say top 40. Okay, Toby Mac is also a contemporary Christian artist who does kind of like a funky soul R&B type vibe. Okay, so what's the probability of event A equal to? The probability of playing a Miley Cyrus song in Mrs. Minnick's car. 1 out of 6. So let's say that there's 10 songs here, 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 there's 10 songs here. And on the old Miley, how many of those would have been would have been country on an album. 4, is that fair to say? 4 out of the 10 are country? Okay. 4 country and 6 pop. Okay. So what's the probability of event B? The probability of event B is 4 out of 60, which would reduce down to 1/15. What's the probability of event B given event A? In other words, we assume that we picked Miley's CD. What's the probability of event B given event A? It's 4 out of the 10, right? Nice, good call, good looking out. It's 4 out of 10, which is 2/5. So my question is event A and event B, are events A and B independent of each other? Events A and B are not independent. For them to be independent, the probability of B given A would have to be the same thing as just the probability of B. Does that make sense? We're doing all right? So what are we singing? In honor of Miley, maybe we should sing, "We can't stop, we won't stop." So anyway, that's it. It's been real. It's been fun. What are we singing? Any shout outs? Shout out to Brittany Thornton. To who? Sang Thang. Okay, whatever that means. Tippecanoe and Tyler too gets a shout out. And Sips. It's been real. It's been fun. Summer gets a shout out. I'm just going to leave an open mic for the last minute if anybody wants to come up and give a shout out because we got about another minute or two of recording.
Shout out to Pusha T. Twisted Truth giving a shout out to Saint Dank.
The future Mr. Minnick gets a shout out.